Welcome to Math 119, Chapter 1.9, where we're talking about solving radical and rational expressions. So first up, let's get warmed up. So pause the video and see what you could come up with these first two. So first thing we're going to do is simplify. So simplifying a rational is when we get to start to factor. So looking at a GCF to factor. So notice that they both have an x squared in common. So by taking out that x squared, you're left with x plus 3. Now the below does not have a GCF, but we can still factor this one. And this one is a simple factoring because your leading coefficient is a positive 1. So we're looking at factors of 15 or negative 15, which is 1 and 15 and 3 and 5. And of those factors, what can make a negative 2? Well, we can have a negative 2 if we add a positive 3 with a negative 5. And if we are to multiply those two back together, we'll get a negative 15. So with those factors that we've just found, we said x plus 3 and an x minus 5, right? So here, when we go to simplify, right? Simplifying means that we can cancel out factors. And typically when you go to cancel out one of your factors, right, you do 1 for 1, you have the same thing above as you do below. You typically make a whole. So then we get x squared over x minus 5. Now this is going to come in handy when we talk about solving rational equations. So just think about what these warm-ups are going to give you in terms of a sneak peek for this chapter to come, or this section to come. Now solving, right? Solving, we can do this many, many different ways. So one method you could have chosen is if we're trying to solve, right? We're trying to get your variable out of the denominator. So one of your ways that you can do it is just by multiplying your x out of the denominator, right? What you do to one side, you then do to the other. Now on that left-hand side, by multiplying it out, the quickest way to get things out of a denominator is to multiply it out. So you are left with a 3 over 5, because your x is canceled, is equal to x. So this is the fastest way to do it. Now let's say you didn't multiply by just your x. Instead, you multiplied by perhaps your whole 5x. So you multiplied that over. Not a big deal. You're just left with 3 is equal to 5x. And then from there, noticing that your coefficient is attached directly to your variable through multiplication. So then dividing out that 5. And you're left with the same answer. Now, another way, if you wanted to, and there's so many different ways. These are just a few ways that I normally see students in class. So maybe you're going to connect with one of these ways, or maybe maybe you chose one of the ways and it didn't quite go right. I don't know. Who knows? Just some ways that you can try. Another way, instead of multiplying things out, what you can do is get a common denominator. So for example, this one has a denominator of 1. So what common denominator could we have? Right? Well, if we have a denominator of 5x, that would allow it to have an equal denominator, which if you wanted to from here, we talked about solving back in, I want to say it was chapter 1.8 and again in 1.6 and 1.4. If we wanted to, definitely 1.4. But if we wanted to, right, to get your denominator to then go away, we're just going to multiply it throughout. Now, because you have it on the same side, right, we'll in fact end up just ignoring those denominators because they're going to cancel, and then you're back to where you started. So these are just a couple methods that you might see. There's lots of them out there. So what we're going to be doing in our next example 1 is kind of a combination. So step 1, when you go to solve rational equations, the first thing you want to do before you get started is to factor. So first step, factor. And then simplify. Can anything cancel? And then the last one, step 3, is to isolate a variable. So what we're going to be seeing is these two same ideas coming down into your next examples. So first step, we said, okay, step 1, let's go ahead and factor. Well, we already factored that left-hand side. And looking at the right-hand side, unfortunately, nothing factors, or I guess nothing has to factor, right? So we said, okay, well, we factored, we simplified, oops, so sorry, x squared all over x minus 5 is equal to 4x plus 5 over x minus 5. Now, what do you notice now about your denominator? Well, in your denominator, right, is the same exact thing. So we actually have equal bases. So whether or not we're recognizing that when you have an equal base and we're asked to solve, we can just ignore your bases. Or you can just say, okay, well, I want to multiply my base out. And what that does is just it allows us to cancel these out. And you're left with just your numerator. The reason for that is because now your numerators are equally balanced on both sides with the same common denominator. So now, have you seen a problem set up like this? Hopefully, yes, right? So at this point in time, since it's not a linear, since it has a degree, not just of 1, but of 2, our next game plan should be to simplify. So the first step we did, we said we're going to factor. We're going to get a common denominator. And now we're going to solve by factoring. So this is directly from 1.8, right? Where one side is set equal to 0. Now, is it easier to set this side equal to 0 and drag over this one, or this side to be 0 and drag those two over? Well, if you do drag this negative x squared over, then you're left with a negative leading coefficient, which if we are going to factor, be sure to factor out your negative before you get started. So what's a little bit easier is to bring over the other terms to one side. That way we avoid having a negative leading coefficient. From here, we can look at your factors. Let's see. So if you can pause the video before I show you the answer to the factoring. We get x minus 5 and an x plus 1 is equal to 0. So therefore, x is equal to 5 and x is equal to negative 1. Now, before we say, hey, we are totally, completely done, right? Let's take a look at your domain. So going back to chapter 1.4, where we talked all about how to find your domain of these rational functions, we said anytime we cancel, we're going to create a what? Well, we're going to create a hole. So where is the hole located at? Well, if it's at x plus 3, right? So that means we're going to do a sign change. So set it equal to 0, and it's now really x is equal to negative 3. So there's a hole for your x value at x is equal to negative 3. Then what else what other restriction do you have? Well, we also have a restriction anytime it comes to your denominator, right? Denominators, right? What number is not allowed underneath any sort of division sign. So we cannot divide by 0. So that just means that x minus 5 cannot be equal to 0. This is your vertical asymptote. So you have a vertical asymptote when x is equal to 5. So if we were to do it on your number line, get a visual for it, we got -3 from the whole and 5 from your asymptote. Our domain should look like -infinity to -3, union -3 to 5, union 5 to infinity. Now, do you see a problem with your domain and your final answer? Well, your final answer should have been right here. But we said what in comparison with your domain? What is the issue? We said x cannot be equal to 5. If we pick this 5 and if we check by putting it back in, 5 minus 5 and 5 minus 5 is going to equal a 0. So you end up causing an undefined answer. So that just means your only answer will be -1. So this is not applicable because it'll give you an undefined solution. So always check and verify with your domain after those solutions have come out, because these are the numbers that we want to avoid. Now let's try again with B. Again, there are lots and lots of different ways we can accomplish one that looks like this. If we take kind of a similar tactic to what we did before, where we're talking about having a common denominator, right? Well, a common denominator over 1, that would be, well, this whole thing would have that same common denominator. So this could be one method. If you see a variation like this, where it's a whole number, it's on the other side. Even if it was on the other side, you could still say, okay, maybe I want to move it over first. Sure, still over 1 now. So one method you can do is create the same base all over 5x minus 1 is equal to 0. And again, we talked about not going backwards by canceling these two problems out. That would be inaccurate. It also just takes you all the way back, right? So you work so hard to get here, do not work backwards. Now to get your denominator out, we can multiply it to the other side. It cancels on this side, and then it multiplies by 0. Or again, if you're recognizing, okay, well, we're solving and they both have a common denominator and everything has the common denominator, then they can just x out. 3x squared minus 5x plus 1, just distributing in that negative throughout your problem. And again, you're left with a quadratic. So one more time, see if it's factorable. So factors of 3 that can get you to a -5. Unfortunately, this one is not factorable, which means what are we going to have to do? Well, we have your quadratic equation, or sorry, quadratic formula. So x is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. So plugging in what we have using parentheses to your advantage. We end up with 5 plus or minus the square root of 25 minus 12 all over 6. So it's equal to 5 plus or minus the square root of 13 over 6. And unfortunately, nothing else simplifies. So we're going to have to trust that these two are your solutions here. Now, there is that another method, keep in mind. Well, actually, if we talk about your denominator here for a second, if we're looking at your denominator, not denominator, domain, right? Starting with your domain, well, we had two functions or two terms. Is there any restriction when it came to this -1 or this -1? No. However, you do have your variable in the denominator, which is going to cause that undefined answer. So we can set 5x minus 1 equal to 0 because we don't want it equal to 0 down below. So when x is equal to positive 1/5, this will cause that 0 in the denominator. So your domain here is any number but 1/5. So we just want to skip over that value. So as long as your solution is not 1/5, then you are totally fine with your answer. Go. Now, if you wanted to, you could have done it a little differently. If you wanted to, you can move that 1 over to the other side. And then just like you did over here, trying to get, or sorry, I should say over here, kind of these other two methods, trying to get your variable out of the denominator. Instead, we can't just multiply everything by x. It has to be this whole thing multiplied by x. So we can say 5x minus 1 on one side, and what you do to 1, you do to the other side. And that'll allow us to cancel this value over here, or that term. You're left with x squared, or sorry, 3x squared is equal to 5x minus 1. And then in this case, we would just have to bring all of your terms over to one side. So it just kind of depends on the way that your mind works. No one way is better than the other. Just practice some of these, get really used to them. I will say I am a big, big, big fan of this one here. So you might be seeing it on a test or a quiz pretty soon. Something that looks kind of like a complicated mess to begin with. And then the more you work on it, the better it looks, right? You already had a common denominator, less work for you. Just ignore your denominators. Okay. Now below it does say look for extraneous solutions. Well, what are extraneous solutions? Extraneous, right? Think about the word extra. It's an extra solution that looks like it's going to work, but it doesn't work. So solutions that do not really work within the domain. Just like that +5 did, it came out, it looked like these were really promising answers or solutions or x-intercepts. And then if we were to go back and check our answers with it, it's going to cause us an issue, usually with an undefined response. Now, where can these extraneous solutions occur? Well, they occur typically, not always, but typically when you're multiplying both sides by a variable, or if you are squaring both sides. That will cause an extraneous solution. So that takes care of the rational expression solving. Now let's take a look at what it looks like with your roots, with your radicals. So can you try out, before you get started with anything and anything complicated, can you just try this quick example solving? Well, you'll notice that you have the square root and then on the other side is just an actual number. Now this variation is really nice because all that it takes to undo the square root is to do what? Well, to undo a square root, you get to square both sides. This will allow us to just rewrite our expression without our square root sign, and then 2 squared is 4, and then we can go ahead and solve. Perhaps you subtract 5 from both sides. So then x is equal to 1. Now, always check your solutions, especially because after learning about what an extraneous solution is, a lot of the cases that you're going to be seeing, especially with radicals, will come up with more extraneous solutions on this end. So check solutions. So if we know that x is equal to 1, we can just plug that back in on one side. So you have, let's see, 5 minus, or the square root of 4 is equal to 2. So 2 is equal to 2, and that is a true, correct response. So it just means that this is your real solution. However, we will be seeing radicals that have multiple solutions, or so they might appear. Now, how many solutions do radical expressions have? Well, based on their graph, if this is just the graph itself, right? Well, how many solutions, being another word for x-intercepts, how many x-intercepts do you have? Well, you have one solution, or one x-intercept. So be super cautious if you do have 2 solutions for your radicals. Check both of them, because more often than not, you're going to come up with a negative or an extraneous solution. So radicals should have one solution. So that being said, let's take a look at example 2. Now this quick example, this is great for anytime you have just no other variables involved, or at least no other x variables to appear other than the one that's on the other side, right? And again, if this 2, we don't want to square our values too early, because otherwise we're going to have to FOIL. So let's, for example, say we had a variation that says 5 minus x under a square root minus 2 is equal to 0, right? Before you square it, because if you square it here, you're going to have to FOIL this out, because there are 2 of them based on the way you decided to square. Squaring too early can get a little complicated. So instead, add anything that's on the outside over to the other side. Even if it's a coefficient, bring it over to the other side first, and then you square it. Bring all constants and coefficients to one side before squaring. So that kind of goes hand in hand with this one over here, right? You can see that there is a -1 on the other side, right? We want to get your square root sign all alone. So step 1, we are going to isolate the radical. So isolate your radical. So that just means we have to bring that 1 over to the other side. That way we don't have to get too crazy when it comes to FOILing. So now that it's on one side, step 2, we're then going to square both sides. So in this case, we're going to square both sides now because it's much easier to FOIL using this binomial as opposed to FOILing with a radical out in front. So on one side, your radical drops, and on the other side, we are forced to FOIL. And what's nice about these is that the process is the same each and every time. Bring any constants over, bring all your variables over so that your radical is alone. You square it, you FOIL, and then you start to simplify. So you have 1 minus x is equal to x squared plus 2x plus 1. And then we can start to solve or start to combine. So perhaps bringing these over, so subtracting 1, adding an x. So you're left with 0 on one side, x squared plus 3x, and that's it. Now, when it is any sort of polynomial, so as long as it's not linear, you're going to be going and thinking about factoring. So to factor, you're looking for a GCF, and then you get to solve. So x is equal to 0 and x is equal to -3. Now we just talked about checking your solutions, right? You should only have one solution, yet it looks like there are two here. So that just means one of them is extraneous. So step 3, check solutions. So from your equation, so checking your solutions, one of them when x is equal to 0, and the other one when x is equal to -3. Now we're going to check from the very, very beginning. So taking the original equation, we had the square root of 1 minus x minus 1 is equal to, again, x. And we're going to do that one again here on the other side. So again, over here. So putting in a 0, putting in a -3, and let's see what comes out. So we get the square root of 1 minus 1 is equal to 0. So square root of 1 is 1, minus 1 is equal to 0. So 0 is equal to 0. So this one we know to be true, which means the other one most likely is false. So let's take a look. The square root of 1 plus 3 minus 1. So the square root of 4 minus 1, 2 minus 1 is equal to 1. Oops. Which is equal to -3. Now, is that true? 1 is equal to -3? No. So right away, this is your extraneous solution. So not okay. So that's your first variation, is if this you have the radical, only one radical. I'm so sorry. Now another one is if you do have two radicals. I do have a worksheet that goes along in this one, which in class will kind of go one for one. Otherwise, after this video, I would go ahead and watch the simplify or solving radicals. I want to say that video is called. That kind of helps us through some of these process with just a little bit more practice. All right, so your second variation is if you have two radical signs. So in this case, what we're going to do when there are two square roots or any sort of root, we're going to bring one to one side. It doesn't matter which one. You typically just need to bring one of them over. So let's just subtract the second one over to the other side. So you're left with x plus 1 under a square root is equal to 1 minus the square root of x plus 2. So once you bring it to one side, so bring one root to one side. Now we get to square both sides. So now we get to square both sides. Now the reason why we wanted to bring one of your radicals over is that it does make it the process a little bit easier because now you only have to worry about foiling with a square root sign only once. I apologize with my dog. So when we go to FOIL, we're just writing out 2 of these. So we can ignore the left-hand side for now. Now, when we go to FOIL on the other side, the right side, we're just gonna go super slow. So we have 1 times 1, which is just 1. And then we have 1 times this negative radical, which hopefully I can just write the radical at this point. And then 1 more. So this negative radical times 1 for another negative radical. And then lastly, you got that double radical. So you have a negative square root of x plus 2. Let's see. I'll just write them next to each other. So now we get to combine your terms. So again, ignoring that one side, then we have 1 minus, and because we are subtracting both and there's 2 of them, we now have 2 of these x plus 2's underneath that radical sign. Now the other one, right, your signs at the very least we can take care of. We have negative times a negative, so your next term is going to be positive. Now these, because you're multiplying them, you actually have a double amount of this radical. So you actually have the square of this radical. Now what's really nice in this variation at this point is that because you are still under and working with the square root, and this is really squared, it's actually going to get rid of this term or this radical altogether. So you're left with x plus 2. So now we can go ahead and combine your like terms. So you have x plus 3 minus 2 square root of x plus 1. So at this point, we're going to one more time get the radical alone to one side. So let's bring over your x. Let's bring over your 3. So you're left with negative 2 is equal to negative 2 square root x plus 2. It's not alone. You still have a negative 2 as a coefficient. So let's go ahead and divide by negative 2. So your 1 is equal to square root of x plus 2. So at this point, how do we undo your radical? Well, now we get to square one more time. So squaring both sides, you're left with 1 is equal to x plus 2. So now x is equal to, a negative 1. Now we can go ahead and check your solutions by putting it back in So check solution. Making sure that our habits are really strong, seeing if this one is extraneous. So we have -1 plus 1 plus the square root of 1 plus 2 is equal to 1. So now we have the square root of 0 plus the square root of 3, which is equal to 1. Oh, so sorry. These aren't, that one should have been a negative. Oops. That's a negative. There you go, 1. So the square root of 0 is 0, and the square root of 1 is 1. So you have 1 is equal to 1, which is a true statement. So this is a real solution. So that one works for us. So this is probably the hardest variation, is if you have two radicals and a constant. So just to kind of summarize one more time, you're going to bring one of these two over. You're going to square both sides. You're going to FOIL. You're going to get your radical alone. And then one more time, square your sides. Okay. Now, lastly, let's take a look at your rational exponents. So with your rational exponents, you might see something that we're asked to solve, and it looks very elementary, at times at least, and they're actually kind of quick and easy, or fairly easy perhaps, is if you have any sort of radical, right? Recall that back in chapter 1.2, we learned how to rewrite these expressions with a fractional exponent. So how would you rewrite this particular one? Well, you have x to the a over b. So that being said, can you try to write this one as a radical? Well, we start with your x. Your 5 goes on your radical, and your 4 goes on top of your variable. Now you could also rewrite it as the 5th root of x to the 4. Now these two are interchangeable because sometimes it's going to be a little bit easier to take do it to the 4th power and then radicalize it to 5th, or perhaps you want to take the 5th root of your variable and then do it to the 4th power. So let's see, do I want to give you a quick example? Yeah. So I have something on my sheet that says I might want to give you something else. Oh, yeah. Okay. So before we launch into example 3, can I give you an extra example? So let's do something like x squared cubed root is equal to 1. So how would you go about undoing, or getting, not undoing, but how do you go about solving this? Well, in order to solve it, right, it's kind of that step by step. So the first thing you might want to consider, having it written in this way, well, to undo your cubed root, what can you do? Well, to undo a cube, you're going to cube both sides. That will eliminate your cube and your cube root. So then you're left with x squared is equal to 1 to the 3rd power, which, yes, I know it's going to be 1, but I'm going to keep that there just for a moment. And then how do you undo this square? Well, then you're going to square root it, right? What you do to one side, you do to the other side. So it cancels once more. So you're left with x is equal to the square root of 1 cubed. Now, how does that compare to what you started with? Because what you started with was the cubed root of x squared, and you finished with the square root of 1 cubed. Well, think about rewriting this as your fractional exponent. Same thing here. 1 to the 3 over 2. They are what of each other? They are reciprocals of each other. 3 over 2, 2 over 3. So when solving with rational exponents, we can use the reciprocal exponents to help undo these obstacles. So with that being said, can you try out this first example? Well, when it comes to example 3, part A, we notice that this 9 is kind of hanging out there, and it's kind of hard to do it all together because then you're going to have to start to FOIL. So instead, let's kick the 9 across the other side. So you have x to the 2/3 is equal to positive 9. So now what can we do? Well, to multiply by the reciprocal, we can multiply by 3 and divide by 2. That will allow us to cancel this 3 and this 2. And what you do to one side, you do to the other side. So you're left with x is equal to 9 to the 3 over 2. But what does that equal? Can we write it back into the, what is it called? The radical expression? Well, if we have 9, right, what goes on the outside? A square. And what goes on the 9? 3. So now, is it easier to cube the 9 and then square root it? Because 9 squared is 81. Do you really want to multiply it again to another 9? Not bad, not impossible. We can certainly do it, right? But then we have this bigger number that we then have to square. I don't know what that is. So instead, let's try and rewrite this one. Perhaps we decide to take the square of 9, something we know how to do easily, and then cube it. So the cubed root, the square root of 9 is 3, and 3 squared is 27. So sometimes the path is clear. It might be easier to do it. It might be easier to do your radical first and then your exponent, or sometimes your exponent and then your radical, and other times it really doesn't matter. So just be strategic about how to structure your answer as you follow through. All right, so now we have something like this. We have 32x squared minus 32x plus 17 all to the 1/4 is equal to 3. So again, this whole thing having that fractional exponent, this 1/4 is really considered the 4th root. So how do you undo the 4th root? Well, you're going to take it all to the 4th power. Now, what you do to one side, you do to the other side. That's again going to allow you to cancel. So we have 32x squared minus 32x plus 17 is now equal to 81. Now, have we seen something kind of like this? Hopefully, yes. Back in chapter 1.8, we learned how to solve quadratics. So let's go ahead and bring this 81 to the other side. So you have 32x squared minus 3x, 32x, I left off a 2, minus 64 is equal to 0. Now, if these are awfully big numbers, typically there's something that you can factor out. So look for a GCF. 32, so then we're left with x squared minus x minus 2 is equal to 0. That 32, you can either hang on to it, you could divide it out, because we are talking about solving here. Factoring, we have -2 and a +1. So then x is equal to 2 and x is equal to -1. Now we do not need to set 32 equal to 0 here, just as we did over here. because 0 is equal to 32 makes no sense. So unless it has a variable to it, we're not going to be so worried about the GCF. Okay. All right. And I do have to say, I think I left something off here. What did we say you have to do anytime you make your own square root sign? So when you make your own square root sign by hand, don't forget to do that plus or minus sign because it does matter for us. All right, let's take a look at applications. So in this example, we're going to be asked to solve for a certain variable. So what this is called is actually what are these called? What are these called? So in example 4, we're going to be asked to solve for a particular variable. These are called literal equations. I do have another video just kind of walking us through lots and lots of problems on just how to solve for some of these, but think about a game plan as just doing the opposite action of your variable. So it says the speed required for an object to escape from the gravitational pull of a planet is called escape speed. The escape speed is given by the equation below, where V sub E is an escape speed. G is gravitational constant. M is the planet, I think that should say planet mass, not pass. And R is the radius of the planet. Solve for R. So if we are trying to get this particular variable, you have to be aware of any sort of grouping, whether that be an absolute value sign, a square root sign, any sort of parentheses with an exponent. We want to work on those first before we can go on the inside. So with us having a square root, the first action we want to do is to get rid of the square root. How do we get rid of a square root? We square everything. So you're left with V sub E squared is equal to 2G times M over R. Now, while there are very many ways to solve this, the quickest way, right? How do you get your variable out of the denominator? Well, if it's doing the dividing, what is the opposite of division? Multiplication. So we can go ahead and multiply R to both sides. And so you have 2GM on one side. Now we're trying to solve for R. So again, trying to get it alone, it's now attached to your velocity, at least, yeah, your escape speed by multiplication. So the opposite of multiplication is division. So you have R is equal to 2GM over VE squared. Now that is solving for your R. It's all alone on one side. It has no other constant or coefficient other than 1. Now you may have been tempted after you square it. So some students that I see decide to multiply, divide by GM. So they kind of do it like this, or they slowly do it. They do G, and then they do M, and then they do 2. Very, very complicated, very confusing, and you can kind of get lost in it. But let's say you at least divided by this whole thing, right? Divide by 2GM. But you're still left with R in the denominator. Because this division sign here, you're really just dividing 2GM or multiplying by a 1 over in this amount, right? So you still have 1 on top of r, in which case we are going to have to perform the reciprocal, right? You have really r in the denominator and you need it in the numerator. So by changing its location, by flipping it up, what we're going to do is then flip this other side upside down. So you have 2gm over VE squared is equal to R. So this uses the reciprocal property or rule. So in case you kind of get stuck like this, you're almost there. You have R on one side. It has no other coefficient, but it's not in the numerator. So just flip it upside down.